So we talked about right-angled triangles with trig yesterday, angles between 0 and 90 degrees. But of course, angles could be any size, so angles could be any magnitude. How do we deal with it? If I just draw up our unit circle there, and I've labelled it in degrees there, 0 degrees starting at the positive, and we tend to go around anti-clockwise, so 90, 180, and so on. The quadrants of the number plane, just as a reminder, where they're both positive, we call that quadrant 1. Then again, going around anti-clockwise, quadrant 2, 3, and 4. Now, what we have to do, when we've got an angle of any magnitude, we have to work out what is its equivalent acute angle. And so we draw in right-angled triangles in each of the quadrants like so. I think of it as the butterfly, if you like. But there's our acute angles. There. So theta is representing the acute angle in the different quadrants. So in quadrant 1, everything's fine because angles are between 0 and 90 degrees, and so we haven't got a problem. But when we're in quadrant 2, it's going to be 180 minus the acute angle. Because theta, here it is, so 180 is obviously a straight line. We're starting over here at 0, so it must be 180 minus whatever the acute angle is. So to work out whether sine's positive, negative, and so on, we have a look at it and look at our triangle, and we say, well, opposites, well, the opposite would be the y value, that's positive, over hypotenuse. Well, the hypotenuse is just a distance. So that's always positive. So positive over positive, so sine would be positive in the second quadrant. If we did cosine, the adjacent would be the x value, which is a negative number, over the hypotenuse, which is positive. So cosine is negative in the second quadrant. And with tan, opposite over adjacent would give us a positive number, the y value, over a negative number, the x value, and that's why tan's negative in the second quadrant. In the third quadrant, so now, again, starting at 0, going around, we'd get 180 plus the acute angle. And we could do the same sort of thing, and we work out, well, hang on, sine would be negative in the third quadrant, cosine would be negative as well, and tan is positive. And then we get to our fourth quadrant, start at 0, go all the way around, well, that would be 360 minus the acute angle. And sine turns out to be negative, cosine's positive now, and tan is negative. There's all sorts of different ways people have to remember which ones are positive, so ASTC, all stations to central, all those sorts of ideas. Remembering, okay, which quadrants are they positive? So if we had to find the sine of 260, now I'm talking about days before calculators, I suppose. And what we used to have, we had these wonderful things called mathematical tables. There's some ancient ones over there on the wall. And you only had tables for between 0 and 90 degrees. So if you had to work out the sine of 260, you'd say, well, 260, that's in the third quadrant, because the third quadrant goes from 180 to 270. So I know sine is negative. Its equivalent acute angle, well, third quadrant would be 180 plus what gives me 260, 80 degrees. I could then go and look up the table for 80 degrees, and I know it's the negative of that answer. Of course, you've got calculators, so you don't have to worry about that now, but that's where it all comes from. So we get negative 0.9848. So tan 220, also in the third quadrant, we would say, oh, hang on, tan's positive in the third quadrant. The equivalent acute angle would be 40 degrees in this case. And we'd look up tan 40 and there'd be the answer. Secant, well, secant is the reciprocal of cosine. So if I'm talking 105 degrees, 105 is in the second quadrant. Cosine's negative, so its reciprocal secant must also be negative, and the equivalent acute angle would be 75. So I could go and work that one out. 430, so I've gone past 360. Well, all I do with numbers bigger than 360 is I just keep taking 360 off until I get an answer between 0 and 360, and then deal with that one. Well, in this case, I go straight to an acute angle, because 430 minus 360 gives me 70. So it's an acute angle. Bingo, I've got the answer. Cosine 70. course, you could have negative angles. Negative angles just means instead of going around anti-clockwise, you're going around clockwise. So negative 67, if I was going around clockwise 67, that would be the same as going around anti-clockwise 293. It's the fourth quadrant. Tan's negative in the fourth quadrant. The equivalent acute angle is 67 degrees, so it would be the negative of tan 67. Now, whilst, as I say, you got your calculators, it's still good to know how we get those, because when we are doing equations, we have to put this information together to come up with all possible solutions. So a little question like this. Okay, what would the coordinates of P be? All we know is that angle is 30, and the radius of the circle is 5. Well, I could create that right angled triangle. And I know that the x value over 5 would give me the cosine of 30. I know the cosine of 30, that's one of our exact ones. So the cosine of 30 was root 3 on 2. So we get the x value is 5 root 3 on 2. And the y value on 5 would be the sine of 30. Sine of 30 was half. So we have 5 on 2. And there's our coordinates for P. All right, but what happens on the boundaries themselves? So at 0, 90, 180, 270, and if I kept going, 360, and so on. Well, how I can create it is by drawing a fictitious triangle. Here's my triangle. I'm going to say that angle there is 0. And then by the angle sum of a triangle, that means the other angle must be 90 degrees. Now, the base I'm going to give 1, but if that angle is 0, that means the height of my triangle must be 0, because it hasn't gone up any. And then by Pythagoras, I could work out the hypotenuse is 1. So, of course, this triangle doesn't exist, but I can then read off the values for 0 and 90 to see what the boundary values are. So, 0... sine of 0 would be 0, opposite over hypotenuse. Cosine of 0 is 1, adjacent over hypotenuse. Tan of 0 is 0, opposite over adjacent. 90 degrees reading off. Sine of 90 is 1, cos 90 0. Tan of 90 we get 1 on 0. Well, that's undefined. When we're drawing our tan graph, we'll get a vertical asymptote there. Okay. So 180, what's going to happen over at 180? Are we in the second quadrant or are we in the third quadrant? Well, we're on the boundary of both. So what I say is this, well, sine of 180, I could say it's in the second quadrant. And the acute angle would be 0. So it would be the equivalent of the sine of 0, which is 0. And it would be positive. Or I could say it's in the third quadrant, and in the third quadrant it's negative, but the acute angle is 0, so negative 0, it's still 0. Cosine would work out to be negative 1, because in the second quadrant cosine's negative, and in the third quadrant cosine's negative as well. And tan of 180, again, would turn out to be 0, similar reasoning to the sine one. 270, we'll get negative 1, 0, negative undefined, well, still undefined, and then we're back to 0 or 360. Of course, again, you have a calculator, so it makes life very easy. You could just go, oh, what's the sine of 0? Oh, 0, fantastic. And if it was something like tan of 90, you go, oh, what's the tan of 90? Oh, error, must be undefined. But anyway, that's a way we can work them out if we didn't happen to have our calculator handy. All right, so what do our graphs look like? If you're going to draw a trig graph, it's a good idea to plot those boundary values and then draw the graph from there. So let's do sine. Now, it went up to 1 and down to -1, our values. That's the range of a sine graph. It'll always be in between -1 and 1, our answers. I'm going to mark off all the boundary points, so every 90 degrees, although I'm being a bit lazy there, I'm only labelling every 180, but I've marked off every 90. I'll go backwards as well. So when I'm drawing sine, I always start at 0 and go, well, where does 0? It starts at the origin. Then at 90 degrees, it goes to 1. And then I just plot in the pattern. It then goes down to 0, -1, and then it just follows that pattern, and then follows that pattern backwards as well. And we've just got to draw a nice, neat graph. Now remember, we're not playing dot to dot here. It's going to be a curve, not a zigzag. So we end up with something like that. There's y equals sine x. So let's say we can look at that and go, oh yeah, domain's all real x, there's no breaks in that whatsoever. The range is in between -1 and 1. The other interesting piece of information, for trig graphs, we have a thing called period. And period is simply how long till the curve repeats. So you might look at it and think it's 180, because you say, well, hang on, I start at 0, and at 180 I'm at 0 again. But you have to be going in the same direction. So at 0 I'm going up, at 180 I'm going down. It's not until I get to 360 that I'm going in the same direction again. So the period's 360. Look at the symmetry. We've got an odd function there. If you were to rotate that graph 180 degrees, you get the same picture. So that means if I want to work out the sine of negative x, I could use the fact that it's an odd function and just say, oh well, it'll be the same as minus the sine of x. Okay, let's have a look at cosine. Now cosine and sine are basically the same graph. So remember, one's the complement of the other. It just means it's been shifted 90 degrees. So let's plot this in and we'll see that. Now, cosine of 0, we start up at 1. And then we go down to 0. And again, that pattern then continues. So we'll plot all those and we'll go backwards as well. And we'll draw in our cosine graph. And we can see, yeah, it is the same picture, but the cosine graph has been shifted 90 degrees. So whether you think of it as sine has been shifted 90 to the right from cosine, or cosine has been shifted 90 to the left from sine, I mean, it's a 90 degree shift. Which means its domain and range is going to be exactly the same. So domain's all real x, range is in between -1 and 1, period is 360, but now look at the symmetry of this one. It's not an odd function anymore. It's now an even function. So that means if I wanted to work out the cosine of negative x, it'll be exactly the same as the cosine of x. Okay, let's do tan. At 0, it's 0. At 90 degrees, it was undefined. So I've got an asymptote. And then that pattern repeats. So 0, asymptote, 0, asymptote, 0, asymptote, 0. Go back the other way. Asymptote, 0, asymptote, 0. What do we know about asymptotes? We bend towards the asymptote. But where do I put it? We know that in the first quadrant, so between 0 and 90, the tan curve is positive. And if I'm bending towards the asymptote, I must be coming down like that. So I end up with something like that. And that gets repeated in between all of those asymptotes. So there, whoop, next one, just half of that one. And there's our tan graph. When you're drawing this, the thing to watch out for, that should be 45 degrees. Don't draw it like a cubic. It's very tempting to draw a cubic there, but it's not a cubic. That actually is at 45 degrees as it goes through that point. So the domain's quite interesting because there's lots of ones I can't have, hence my rather large box there. So to generalise it, I'll say, well look, it's all real x. I can't have 90, but then every 180 degrees before and after that, I can't have that either. So well, plus 180k, where k is some whole number, some integer. Could be positive, could be negative, but that's where we'll find all those asymptotes. The range is easy, that's just all real y. There's no breaks in it as we go vertically. And the period for this one is only 180. And it takes 180 degrees for this one to repeat. It also has symmetry, if you look at it. This one's got the rotational symmetry. So tan is an odd function. So if you had to find the tan of negative x, you could do the negative the tan x. Our reciprocal graphs, I'm not going to do them all. We're going to do cosecant. Cosecant is the reciprocal of sine. So we said reciprocal graphs. Everywhere there was an x-intercept, that will now become an asymptote. Well, there's my original sine graph. So everywhere there's an x-intercept, they will become asymptotes. Now the point 1, if I turn 1 upside down, I get 1. And if I turn -1 upside down, I get -1. So those peaks are going to change. But what we also said with reciprocal graphs, where the original one is concave down, the new one will be concave up. Where the original one is increasing, the new one will be decreasing. So if our sine curve, if I'm just talking about positive numbers here, but if our sine curve is always below 1, then our cosecant curve should always be above 1. So what we end up getting is a series of U-shapes. They're not parabolas, but they're just U-shapes in between each of those asymptotes. The secant graph would look very much the same, but with a 90-degree shift. The tan graph, well, all these x-intercepts become asymptotes. All of these asymptotes become x-intercepts. And you'll see a reflection. It's a shift of 90 degrees, but there's also a reflection. You'll see the curve go the other way. All right, there we go.